And I believe it's being recorded. Yep, perfect. Actually, has anyone been watching those videos online?
If we need to revise that.
Like I get the email, but I just stopped looking at the emails. Like, I get the email, like, someone's watching it. I'm done with to see who's watching it. All right, so well, we ended with a problem last time, right? We're looking at TNB frame, right?
Yes,
Problem we're looking at was, I believe, RT cosine TI plus sine TI plus DK, right?
yeah,
We
and we
finished that
found,
problem.
we found the unit tangent, the unit normal and the unit binormal. That's where we stopped.
Okay, so we did the matrix then,
Yep, that was the end of the class.
and then we didn't find the curvature, right?
No,
No, so let's just rewrite the equations. Let's do R RT is equal to cosine T of I plus sine T of J plus DK. All right, and then everything we're up to B of T. And we got the square root of 2 over 2, right?
Yep.
And we had sine T of I plus, was it cosine T of
minus.
minus, okay. And was there anything else like
Plus K.
plus K? All right, cool. All right, so if we want to find the curvature is kappa is equal to, let's see, it should be the tangent of T, its magnitude of the tangent of T, or is it it's the derivative, right? If I remember correctly?
Yep, yep,
Derivative, and then it should be R of T, right?
our prime and
And its magnitude as well, right? Perfect, so we have this guy, we have this guy. So that means it should be what, root 2 over 2? Divided by, what was R of T of prime?
the magnitude of that was,
Must have had it backwards.
square root of 2.
It was just the square root of 2, right? Okay, so, oh, this curvature seems to one half then, right? Everyone can get this, right? This is probably the hardest question on the next test. I hope. No, I think getting these are pretty hard. And it depends on the function that Pearson gives you guys. Remember, Pearson's giving you the function, so if it ends up being one of the most complicated functions, I do apologize. Because Pearson is Pearson, they're evil corporation. And what did we agree for the exam? Just make break this on page
11th, yeah.
11/11/2021.
That's correct.
And that's going to be Thursday, right? Next Thursday.
Week from today.
Wow. Okay, all right. Didn't we go through the magnitude of or did we not go through it?
We did, you used it to find the normal vector, it's up back there.
Or maybe we'll quickly go through it again, right? So to get that magnitude of T.
I'm sorry, I'm gonna have to just,
Oh, okay, all right.
I'll take it down.
Yeah. Sorry about that.
No,
That's why I like to finish your problem before the end of class, just so we don't stay to another day and everyone forgets what we did. I even forgot what we did. Okay, all right, so this is kappa, and what else were we supposed to get in this problem?
rho, which is,
Rho, well, is that just a reciprocal?
Yeah.
So it's just a reciprocal, so it's 1 over kappa. So we'll say rho is just equal to 1 over kappa, which means it's gonna be 1 over 1/2. So I know this one's hard. You got this, Joey. What is the answer? 2. That means rho is 2.
the last thing it said was, write the equation of the oscillating plane at t equals pi over 2.
Ah, okay, so I have pi over 2, so that means we're gonna plug in pi over 2 for every one. For t, for n, and for b. So what we're gonna do is we'll have the function, and since we have b already on the board, we'll just look for b of pi over 2.
What is the equation of the oscillating plane again? I don't,
Oh, so the oscillating plane is basically we're gonna have that curvature, right? And then, it's not oscillating plane, it's osculating, right?
osculating. Okay.
Yeah. So that's gonna have a specific point there. And that specific point is going to have a nice, well, it's not really a little circle. So have a nice circle, it's only gonna touch it at one point. Then we're gonna have it pointing towards the radius. And then we're gonna have another one pointing in this direction, which is perpendicular to that. And then the other one's going to be pointing in that direction, which is perpendicular to that. So the oscillating plane is just pointing towards the radius. So what we're looking for is, where's my, anyone see where my airplane went?
No.
No, okay, so here about the airplane. So picture the airplane as it's turning. What is it doing? So it's going straight forward. That right there is going to be pointing towards the actual radius itself. Which n is pointing to the radius, if I remember correctly, right? N is to the radius. T is that direction, and this right here is B. And N controls turning, T controls the direction it's going, and B controls the twisting, right? If I remember correctly. So what the oscillating plane is going to do is it's just pointing to that specific radius, and what we are creating is like this. Think of it as you're creating a tangent circle. So it's just that one specific point on that thing, and it's just we can find it at that specific point in time. So what we're going to do is look at that specific point in time, and we're going to get a bunch of corresponding points that go with it. All right. Any other questions? Cool. All right. So we're going to actually plug in pi over 2. If you plug in pi over 2, what's going to happen? We're going to get sine of pi over 2. And what we can do is we can make sure we do this, right? Because they're going to be components. So we plug it in, sine of pi over 2 is how much? 1, right? So we're going to have 1, or just I. Actually, let's get some order here. So if we do b of pi over 2, its vector, we're going to have square 2 over 2 times the sine of root 2 of pi over 2 times I minus cosine pi over 2 times j plus k. Cool thing is k has nothing, so k is just k. So we're going to find that we're going to get 1, so we're going to have just I minus what's the cosine of pi over 2? 0, so that means there's no j plus k times root 2 over 2. And then we can find t, of pi over 2. And that was √2/2 times what? Was it sine t of I again? Negative sine t of I, that makes sense. And then it has cosine t of j, right? This is minus or plus cosine? Plus, okay. Plus cosine t of j. And then we have, is it just k again? Just k again. So if we plug this in, we're gonna have √2/2. Minus I, right? Plus k. Cosine of pi over 2 becomes 0, 0 drops to j, and this is that vector at that point. And now we're going to calculate the normal one. So let's just kill a few things. Oh, sorry. So we're under test number 3, right? Test 3? Test 3. Eleven, 21. And I said what test 4 is on the 29th, right?
I 30. Yeah.
30, okay, 11:30. I'm sorry. 11:30. The cool thing is about test 4, if you do exceptionally well on test 3, and you do exceptionally well on test 2, you did exceptionally well on test 1, theoretically, you get to show up for test 4?
Yeah.
Not really, right? Because I'm dropping the lowest grade. If you're happy with your grades for test 1, 2, and 3, you can take that day off.
I barely passed.
Yeah.
Okay, okay. Alright, so we're gonna have normal vector, or pi over 2, and that should be the cosine t of I. Negative cosine? Okay, negative cosine t. And then we have plus, is it minus sine t?
Yeah, mine's
Minus,
I had a hard one.
oh, is it?
I don't know.
That's a little bit of work.
From the end, right?
Yeah, and the t is negative sine t, or did I write positive last time? I have negative sine t. Okay, alright.
just
Perfect. And it is no k, right? No k. Plug this in, we're gonna get I. No, we're gonna get 0 I, right? Minus k. And 0 I just goes away to the that yeah. Don't they have WD-40?
no.
Oh, I think that's the garbage, they were just putting around, yeah, just putting the garbage in, the
Yeah.
really sweet rag. So you usually have like very useful. It's like a bottle, small like this, or a little thing like that, it's called WD-40. Most likely your dad has a can.
Everyone does, yeah, it's like if they give like a squeaky door hitch.
Yeah, and it prevents it from squeaking and annoying people, just like the way it was written.
As it comes watching down the hall.
Yeah.
What'd you say?
Oh. Oh, another reason why I was late, we finally got our lab equipment for
Oh, goodness.
for physics. And it's hilarious. The reason why I find it hilarious is because we ordered this material in March. And it's November, and we just got it. So I finally got hydrochloric acid, I got some sodium carbonate. So, we usually do thermodynamics in physics, and we do the gas laws. Gas laws, you can make any gas and then you put it encase it in a bottle, and you see different colors. Hopefully, it works. So I was gonna test it today, and I was like, I'm late, so I ran, I made it here just me. What was it, 2 minutes late, 3 minutes late?
Or,
Just counting, okay, 4 minutes late, sorry. Yeah, you're good. Think we're gonna hit the 15-minute mark, you gotta go left, right?
yes. Is that actually true or not?
That's true, actually. That's,
Well, I see.
that's true for every college. So this. Let's try to keep them in order, so we know we're gonna have √2/2 I plus K. And then we'll have √2/2 I plus K. That's third. Should just be minus J, √2/2 I plus. This is T. That's pi/2. And this is the N at pi/2. I can't even write today. And then B at pi/2. Okay, we can even make the corresponding matrix if we want to, right? Well, glad you asked. Let's say I wanted to avoid going through all those calculations. Let's say we just wanted to calculate just T and N. We calculate just T and N. Isn't it directly easy to take these two right here and figure out what this guy is going to be?
It's the cross product.
Because it's just a cross product. So once you have these two things right here, you can easily find a cross product, and you can find that one like that. And it works for either of them. So if you have T and B, you can easily find N. If you have T and N, you can find B. If you have B and N, you can find T, because they're all related to each other. So it's like a shortcut. The reason why you do that is because you'll get really, really complicated versions that you have to get the cross product of, and then it gets annoying. So yeah, let's see. So I think I wrote it down in my notes as another way. The best thing to do is you have a bunch of tricks up your sleeve, you can do anything. Well, let's just say another way. Because let's suppose that we're only able to get T and N. And going the direction of getting B was long and exhausting. Let's say we were taking a test. Like we will be next week. We're taking that test, and we have to figure out B. We're pressed for time. The last 10 minutes of the test. We saved this question for last because it's a long question, right? So we say to ourselves, oh, well, we have this and this. Well, why not just throw it into a matrix and try to solve it that way? So if we just have T and N, or T and B, let's see which one do I have. And calculate. Okay, the T and B to get N, so let us do T and N to get B. So we're looking for B. We know B is going to be the cross product of T prime cross N prime, right? So if we have a matrix, the matrix that we're going to have, we're going to have a -1, right? -1. J is going to be what value, Jason?
Oh, 0.
0, right? 0. And this guy's going to have a K, which is a 1. And then J itself, that's going to be what? 0, -1, 0. All this multiplied by √2/2, right? And that's our I, that's our J, that's our K. Now, using these two, you can easily find B. Let's do that now. See if you can find B.
We never learned matrix. I mean, I never learned.
Oh, okay. All right. So
T prime, cross N prime.
Earlier you defined it as just T cross N.
oh, okay. T cross it. Okay. All right.
So it's not
Yeah.
fun.
Not prime. Yeah, not prime.
I was like wondering.
Which one's right, positive?
So there's one matrix.
Yeah,
Oh, so
You
you're
mean
saying
like-
you need to see more matrices.
I mean, you have a whole class on it, like one is like doing one and not one.
All right. So let's talk about determinants of matrix. We'll call this a super duper mini lesson. I think that's a really small way of putting super duper mini lesson. You guys could barely see the word, right? Yeah, so it's not a mini lesson because it's super duper. All right, so what we're gonna have is, okay, so if we have A, B, C, D, and we want to find the determinant of that matrix, what we're going to do is we're going to multiply A by D, right? And minus it by B by C. And we need to multiply it by something, yes.
When you say matrix, is that another for determinant? It's the same thing.
No,
I didn't take.
Oh, okay. So, okay, all right, so a matrix has columns and rows. So this right here is going to be height column, this right here is going to be the j column, this right here is going to be the k column. This right here is going to be a row, this right here is going to be a row, this right here is going to be a row. This is a 3 by 3 matrix, as it has 3 columns by 3 rows by 3 columns. This right here is a 2 by 2 matrix, so it has 2 rows, 2 columns. So far, so good. Alright. Then if you want to find the determinant is we're going to multiply this by 1 over, should be A, B, minus C.
And that could be 1.
Determinant.
I don't think you multiply it by anything if it's just a 2 by 2.
Determinant. Yeah.
I don't think you ever learned about one because part is the class product in the method product.
With the algebra, right? Yeah.
The matrix,
I don't know if this is like another way because actually I just did it. And I got the same answer.
It's just a different way of finding the cross product. It's
Yeah.
using it, writing it
But
out.
it's
as-
always a cross product. equation?
Yeah, it was how you use the cross product. So basically, what you look at the I row and you create a 2x2 matrix here.
We'll make it to show us how to do it on the calculator, I think that'll be fun.
Why does someone use a calculator?
Isn't that why you're teaching it? So you use.
Oh, yeah, but remember,
I can solve determinants, but I just didn't know you're like matrix, I don't know what operations matrices, so.
oh, well, yeah, it's okay. So you're gonna learn this all next semester, differential equations. You get like, so it's gonna happen if you have a system, a differential equation, you get to do those system of differential equations. So in the matrix, and you do matrix, operations, and you get the answer. So. So what we take the ith row and times it by that matrix, which is going to be 0 times 0, 1 times -1. And then we subtract the j row, which is going to be -1 over 0, 1, 0. And then the kth row, we add the kth row, which is going to be -1, 0, 0, -1. And we take this determinant right here, we're going to get 0 times 0, which is going to be 0. -1 times 1, which is going to give us a minus -1. And we already see this becomes 1. 1 times I gives us 1i. 1i. 0 times 0, that's going to give us 0j. Minus 0j, you can really see as j drops out. And then we do -1 times -1, which gives us +1 plus +1. And 0 times 0 is 0 times k is just k. So we get 1i plus, not plus, but just 1 plus 1k times square root of 2 over 2, which is this row right here. Any questions about that? Yeah. This is a 3x3 because we have I, J, and K in that. So what we do is when we when we make this, we just cover this row. We're covering this row and this column. This row, this column. We take this 2x2 matrix to get this value right there. And what we do is we take this guy and we cross multiply. We get 0 times 0, which is going to give us 0. Are you throwing that into your calculator?
I'm trying to figure out how to do it.
On your calculator?
Are you supposed to put in for IG?
Well, I don't think you could do IJK on your calculator.
Oh, it's too dark.
It's going to give you a different determinant.
I think you can only take determinants of square matrices.
Yeah. Any questions about that? Or you already know how to do this. You already know that you have to, all you have to do is multiply 0 by 0, you get 0. And you subtract it out whatever you're multiplying by this row. This is 1 times -1, you can make 1. Negative of the negative gives us a positive. Don't worry, I'll do another example for you.
Oh, it's fine.
Well, actually, I did plan to do another example anyway. So. Yeah. But we're still not done with this problem. Because what's the next thing we have to find?
A point like a position. Just RT or R if I were to.
Okay, and what else were we gonna talk? I think I asked for two things.
It's just oscillating plane.
Oh, just the oscillating plane?
Yeah,
Okay, so we just want to find the oscillating plane. How do we find a plane? Let's not even talk about the oscillating plane, just talk about how do we find a plane? Yes, Eric.
By normal vector, it's like the direction numbers of the plane.
Okay, all right, so what do we need then for a plane? We need a point and what else?
The normal,
No, normal vector, right?
which is the binormal.
Binomial, yes. And when it comes to that, we just need a normal vector, right? It's gonna be a linear combination, right? So do we really need to take any of these points right here? Like this one, if you look at it, it comes with one and comes with what, 1, 0, 1 times radical 2/2. But do we need to take the complicated version of it? No, because it's just a plane, which means it's gonna hit all those points. So we're gonna take the easiest normal vector that we can use, right? We don't wanna make our life difficult. Who likes to make their life difficult besides me? Nobody, right? So you wanna take the easiest known thing you can take. So we're gonna take a normal vector, let's just say normal vector. With a specific plane.
So it's gonna be. I just don't have to use. So would we find the plane with respect to one of the values, like the tangent, normal or binormal?
Yeah.
So you can do it.
the oscillating plane is defined as the plane, with the binormal vector perpendicular to it. It's in the textbook. So you always use the binormal vector when they're asking for the plane, because that's always perpendicular to the oscillating plane.
All right, so. What you were asking was if we can use any of these, right?
I'm just not sure if an oscillating plane is just, if it's a plane, it can be many directions, but it's gotta be perpendicular to one of them, obviously.
Yes, but so. What you're asking is if we can use T or N, right?
Well, like if you use coordinate axes like X, Y, Z, they're all perpendicular to the same as T and, right?
Yes, but okay, so, all right, so I think I know what you're talking about. All right, so here's this is the direction of that, right? This right here is the direction of T. This right here is the direction of B.
The B comes straight out of the screen.
Yes, so is there a specific orientation like this? Is the oscillating plane pretty much in line with any theta and perpendicular B?
Yeah,
Yeah, so basically what we're gonna have is, or, can I borrow someone's paper? I will not prepare. Perfect. Thanks, sir. All right, so. Visuals always work.
there's a good picture on page 794 if you've got your book around.
Does everyone bring the book to class?
Yeah.
Oh. It's okay, go ahead. Maybe that picture on my phone, rather than my airplane.
Okay, yeah. So there's three different planes, they have different names.
Yeah,
for the oscillating.
just to give everyone else a visual, I don't have a book. So the tangent is gonna go forward this direction, right? Then the normal is going to be the wings. And then your binormal is going to be, think of it as a tail pointing up. Hopefully that, you can see that visual right there. So we have the tangent going in this direction, then we have the normal going in this direction, and then the binormal is going to be that tail that's coming up like that. Now, the oscillating plane is just going to be something that we can create right here to the binormal. So that binormal is projecting out to the coming towards us. If it's coming towards us, then we could just take a portion of the plane and cut out a nice circle there. Hopefully that makes a perfect visual for you guys.
And the binormal is perpendicular to the osculating.
Yeah.
Yes,
So it'd be almost like where the wings are.
yeah, no, the wings are gonna be
And, right?
the normal vector,
So is the normal vector parallel with the osculating plane?
parallel.
Both,
really say
both the normal vector and the tangent vector lie on the plane of the oscillating.
Okay,
Of the normal. End.
so it would be like the wings, be like the plane that was on the wings.
Yeah.
Like if you visualize the plane as like a paper, so it would lie right there, right?
Yeah.
Wanna look at my book?
Yeah.
Yeah, the book was embedded in my plate.
And then normal, and that's the oscillating force. Binormal is.
Okay, yeah, middle one.
Yeah.
Yeah, so it's the wings.
I don't want to see.
I got it. Why do we need the osculating
Some of the Pearson homework asks you to write it.
plane? Yeah,
Yeah, no, this is more reasons why decided
just
that,
because, yeah, homework.
just because someone knows. So, let's see, what's a good scenario? Pearson works.
Just to get good at derivatives.
It's gonna lead into what we're gonna end up talking about. Not this class, but most likely next class, when we start talking about directional derivatives. Or directional partial derivatives, that's when it's going to become more clear. Which is why I group those two together.
What is it used for?
So. Okay, so suppose we have a nice world sheet, and this is a world sheet that's projecting up in Z. Hopefully you can see that with that picture. So it's projecting up. So if we are looking at a specific point, let's just call this point P. Isn't it safe to say that along this line, there's another point, which we can call P prime? Perfect. And then now what we're going to do is we're going to make a secant line. We're going to suppose another point, which we're going to call point Q. And we're going to have a corresponding Q prime there. So far, so good, right? And what we're going to do is we're eventually going to take these 2 points and we're going to try to squeeze them together. When we squeeze them together, what's gonna eventually happen is they're gonna become the same point, right? That same point is going to be our limit. Okay, let's see. Then we can just call this the limit of that point. I don't think that's doing the normal plane justice.
I guess what I'm trying to ask is like.
A practical application of it.
Yeah, yeah.
I can't think of anything that's perfect to fit that right now.
So it's useless?
No, it's not useless, it's very useful. I just can't think of a good example of why we need it at the moment. Yeah, I'll get back to you on that one.
Okay.
All right. So. We want to find the oscillating plane. So what we need is, we need a normal vector with the specific point on that vector, right?
Yeah.
Because that's how we find plane. So we can take any point on that plane, we can take any vector on that plane, and we can create the oscillating plane. All right, so how do you suppose we do that?
Because you could find a point and find the value of B at that point, and then write it the way we've written vector or planes before with the vector.
Yeah, if you have like the equation of the line,
Yeah.
and you find a point on that line, you probably figure it out, right?
Yeah, the plane is equal to the components of the vector times x minus and the x.
I think if you parameterize the equation of the line, you'll get it like x is equal to something from t.
Well, we were given RT, that's the position vector.
Okay,
You just solve the position vector RT for pi over 2, and then that's your point, and then you already have a vector. You can get an equation for a plane from point to vector.
Yes.
All right. So how do we get the point?
RT, you plug in pi over 2.
Okay, what do you get?
Cosine of t, which is gonna be 0i plus 1j, because it's sine of pi over 2, and then plus tk, so pi over 2k.
That's our point, right? Okay, and everyone sees how we get that. Came straight from the original vector itself. All right, so we have that point. Now the next thing we need is, well, we need B. Well, B is going to be what?
This sine plus tan.
We're going to turn it into a vector, right? And what's that vector going to be?
What numbers here from one?
And then where do we go from there?
Plug it into the standard equation of the line.
Yeah, so it's like the point plus t times the normal vector. Oh, so that's the line number. Yeah, it's that one.
You're saying this is,
Yeah, that's it.
Where A, B, and C are the components of the vector.
not for the plane.
Because for the plane, we don't need that root over 2, we only need a normal vector. So it would work, but
The root
I'm
2
talking, we don't need it.
the root 2 over 2 makes B a unit vector. It's the unit by a normal vector, but we don't actually care about the length, so you can see that.
as long as the direction correct.
Yeah.
Okay, and what do we do from there?
Okay.
So what are we gonna plug in? So A is gonna be what? One. And what's B gonna be? Zero, so B drops out.
Yep.
And what's Z gonna be?
One.
One. And what goes into X, Y, and Z?
So 0, 1, 5, or 2.
So this one dies out. And we're left with just X, right? Plus, that's gonna be what Z minus pi over 2. Well, remember, this needs to be an equation, so we get to set it equal to what? Zero. And then what do? We just make sure that we have our variables on one side and our numbers on the other side. We're gonna have X plus Z is equal to pi over 2. Any questions? Besides, why do we need an oscillating plane?
If we finish the exam.
Okay. Let's see, 625. That's right, it shouldn't take that long. Okay, this is gonna be one for you guys to try. We're gonna have R of T equal to. I can leave it like this, I think you guys can handle it.
Rich. Time again.
Let's line that, and fine, that's good. Yeah. Everybody done, or so we're. Okay. Need more time?
Yeah, I did. Mine has
I think I messed up, I'm sure, make it short cut. So flat,
It fell flat in your face.
not work.
Okay, so if we look for R prime T. That's gonna be a product rule, right? Product rules, we're gonna have, was it e to the T times what? Negative sign T, right? Plus, what? E to the T cosine. And that's the I coordinate, right? And then this one's gonna be the same thing, right? Just gonna be E to the T times cosine T, right? Plus, that's going to be e to the T sine T, right? And that's just going to be the J coordinate. Okay, here. And we're gonna have e to the T, right? So that's just going to be e to the T, right? And so probably put that back to vector notation. If you want to find the magnitude, if you want to find the magnitude of that guy, that's not that hard, is it? The magnitude, let's see. Oh, sorry, what?
square root of 3 times e.
Okay, all right. So I mean, do you need me to show you the steps?
Well, the sign for each term, there's gonna be like a sign for cosine.
Yeah, and then zoom
Times
into the one.
E of T. And then the last one's just gonna be E of T times, E of T squared times 1. So I think without doing calculations, it's just gonna be square root of 3 E of T, right?
Okay, all right, all right. Does everyone see that?
Square root of 3.
It's gonna shoot T, but
I think
You
you
mess
take the
up
square
somewhere.
root of e to the 2t. Square root of e to the 2t is e to the t. Oh,
Yeah.
Okay.
I messed up here, so, oh. Are we supposed to be doing T by N as well? That would how you get B,
I'm sorry?
so, were we supposed to be done with T by N as well?
I think he
Okay,
stopped.
I-
I think he stopped after finding t. Is what he said.
Oh, you stopped and then you just gave up.
Something.
No, I stopped at T by N, that's what I'm working on now.
Oh, you were working on this guy, right?
No, T.
Yeah,
Cross
yeah.
out, that's what-
Oh, so you're on this guy.
that's what I'm-
All right, cool, all right.
Yeah, yeah. I was like, I think I did this way too fast.
I really.
So I did,
don't
right,
know,
I
like,
thought,
this
oh,
is
well, there's an EFT in each term, so you just factor it out and then like, what's that? Shortcut it. And I messed up.
I got
Yeah.
I never.
Yeah,
It's okay. So I messed up, so I don't think it's. Yeah, you get a scalar. Yeah, why is that? Is B, this is not doing that, nothing. This is the binomial vector a vector?
And this is just a
Scalar.
scalar.
Yeah.
So by rules of vectors, if you have a scalar inside your vector, you can just technically
Yeah.
pull it up. And that's just going to give you 1, 2, 3, square root of 3. For those of you that didn't see. you guys can do this, I know you guys are really good at doing that, so I won't do it for you. Unless you need me to. Okay, just check. Alright, so this is going to be basically this entire vector over this value, so maybe you're gonna have root 3 e to the t, all of this under, what is it gonna be? Well, it's just going to be e to the t. So minus e to the t sine of t. Plus e to t, let's leave the negative on the side. Cosine of t. So pi. And then I'm only messing myself up with this capitals there, so it'll be e to the t cosine t plus e to the t sine of t j. These are, they're fun, but they're long and annoying sometimes. And then e to the t. So what happens? E to the t is canceled. Everyone see that. Basically, you can basically, you can just take e to the t out, the e to the t will cancel. So what we're going to get is what we had, kind of like what we had before. But this time, instead of square root of 2 over 2, we're going to get square root of 3 over 3 times minus sine of t plus cosine of t of the I coordinate, and then 1 is going to be at the end, and then we're going to have plus. So let's see. Do we even know? Where are we putting plus? That's going to be cosine of t plus sine of t. Okay. So we see that, right?
Is there a 1 at the end?
Yes. I see it. Oh, it looks like a D now, doesn't it? Yeah, it's on. Perfect. So far, so good. All right, so now if we want to find n of t, we're going to take the derivative of this guy, right? We take the derivative of this guy, what happens? Well, we're going to pull square root of 3 over 3 out, right? And then we're going to have, so it's going to be square root of 3 over 3. And what's the derivative of this right there? What's it mean with negative sine t, you said? Plus what? Minus cosine t. And that's going to be the I. And that is going to be what?
Negative sine t cosine plus cosine. That's 0.
That's 0. Good job.
Magnitude that is still going to be root 3.
Because this is going to be,
That's all of that in there is all gonna go back, still go to 1.
that's going to go to 1. That's going to go to 1.
Well, them combined is equal to 1 in the magnitude. Because you're squaring out the I and you're squaring the J.
Okay, all right,
Or
perfect.
minus, yeah, I mean, it'll, I think you should all go to 1, I'm not sure.
Should be root 2.
Okay. I
And
missed
it's
that.
going to be root 2. And then,
Oh, right, it's actually should be 2, yeah.
so it should be root
I'm
6
doing it
over,
in my head, so, yeah. messed up.
so root 6 over 3.
You want us to keep rationalizing denominator?
Yeah. I think Pearson's gonna want to rationalize the numbers Pearson's discussing.
They don't, they don't.
They don't
They don't care?
They don't care.
Oh, so you don't have to rationalize the denominator. But,
At least on the homework aspect.
And I think on the quizzes, they don't.
and tests, right?
Yeah, they don't care.
Oh, okay, they don't care, then I don't care. All right, cool. All right, so then what are we going to do? We're gonna take this guy and put it over this guy, right? And then what's our final answer for angle T? What is that then?
1/√2.
1/√2?
Times. Yeah. And the I component. Negative sign minus cosine.
So the negative sign of T minus cosine of T, bye-bye. And then comma
Minus nine T.
of J and 0. Perfect. Excellent. I'm feeling confident that I could put a question like this on your test and not cry to it.
As long as it's like, you have time to do it.
Oh, yes, of course, of course. You're gonna have so much time. You're gonna have a limited amount of time.
Unlimited.
I know. Can't give you a limited time. I wish I could. Alright. So finding B, just cross those two. But technically from here, we can find kappa, right?
Yeah.
Let's find kappa, because that's the easy one.
Jared, you got 1/√. I was working on this cross.
Yeah, the cross product is a nasty one. Oh, Lord, put me to sleep. Sure.
What'd you say? I got root 2 over 3. Oh, you got
Look, when you pull this guy up, you see the kappa left over, and so that's 1 plus those 2. You're okay.
Wait, so 1/e is 3 times. Oh, yeah, I wrote it wrong. What did I do?
What'd you get there? I got √2 divided by √3 times E.
√2.
For kappa, so yeah.
So, just like
That's the thing for it, yeah.
that, when you still learn.
Yeah, I remember. That was √2, or 1/√2.
I have root 2 over 3.
Yeah, okay, yeah, so then, yeah, it's canceled. Yes, okay, yes.
It's a
So 640. I'm gonna skip these, that's okay with you. And I'm gonna jump into projectile motion. Okay. Ah. Joey's been waiting for this one forever. Right, Joey? Because he knows how to do it, right? You remember how to do to protect others? Yeah, physically, we knew it, physics.
I made an equation.
I don't know, yeah, I use like kinematic equations.
Alright, so let's talk about projectile motion. So it's gonna be V naught cosine of alpha t in the coordinate plus h plus V naught sine of alpha t minus 1/2 gt squared. And let's just do a j component. Okay. Well, keep it simple, stupid. All right, so of course we know V naught is going to be what? Right, initial velocity. Alpha is basically what? Of inclination.
Inclination.
H is the hard one, right? What's H? Height, right? Height. We'll put in parentheses above. And ooh, this is crazy. What's G? Gravity. Gravity, right? 9.8 to what?
Second square.
Meters per second squared. I like it. What about its feet?
32.2.
Good job. All right, all right. Okay, let's see. Let's just take an example. Okay, so you shoot a rifle. From a 200-foot cliff with an angle of 30 and muzzle velocity of 1,500 feet per second. Just because we're American, we like, yes, sir.
So G is like 32 even, 32.2.
Yeah, let's go with 32. Just even 32. Just because if we do 9.8, we're technically we're not. You do 9.8, you do 9.81. But we'll leave that as 32.
And where are we playing?
Let's see what's the- When it hits the ground. What else I want you to find? The range. Always say max range. Can't even write it. Max range. Max height. We're going to do for argument's sake. Yeah, for argument's sake, impact will velocity. one thing I want you guys to never do, what is the one thing you can never do with a gun?
Straight up.
Point it straight up, of course you're gonna point it at someone.
Yeah.
Yeah, never shoot a gun, never shoot bullets into the sky. Because those bullets have to eventually do. Come back down, when they come back down, they come back down at the rate and almost close to the speed that you shot it at. And that still can take someone's life. They had a cool episode about that in 1,000 Ways to Death. Then we'll see the show 1,000 Ways to Death.
Yeah.
Oh,
I like the game.
there's a game?
No, that's dumb ways to
I'm
die.
next on the show.
Oh, okay.
Actually,
Like a long time ago, there was like it's a movie.
yeah, I remember. It's
It
a
was
lot.
fair, so-
Yeah.
I don't remember it. You're saying it's a long time ago. That makes me feel even old.
I heard a long time ago it's mobile game at the same time. I was like, that's not a long time ago. What do you mean?
Oh, okay. Oh, that hurt my gut right there. Oh, my heart and everything. Okay.
That's a good one.
So, yeah, so that's what the guy did. It was 4th of July. He was intoxicated. He took the gun, shot it up to the sky, came back down over the head.
Must have been pretty straight.
I was gonna say, he's like,
I think what he did was he shot it up like that, and he walked towards, I think, his grill. And his grill was like a few feet away, and when he came back down, it hit him while he was grilling him. Drunkenly, of course.
At least only give him a gas tank. It was a gas.
he died.
It is a true story because all those stories in 1,000 Ways to Die is true.
Yeah, I used to think that until I saw Santa look up into an icicle. I was like, wait a minute, does that fell through his eye? That scared me for a little.
That's just the light that's on the top.
Stalactite.
That scared me like, for a little, I couldn't handle icicle.
Can we just go over it?
Oh, you don't know how to do it?
Oh.
I'm sorry. Oh, whoa. Okay. All right.
Well, I think we're learning about it.
Yeah, no, but I assume that you guys knew what to do.
We're just learning it, so
Please do it.
we haven't done it before. I mean, I've maybe done it a long time ago. It'd be nice to have a refresher.
Of course it is. Oh, we could put Joey on the board because he knows what he's doing, right, Joey?
I can do it. Does it?
No, you never say that. I realize that. I might need a refresher. Because I just go right out there.
Yeah, exactly.
He says he's kind to himself. Kind of makes sense. So-
Honest.
Are we not using geometric equations?
We could use schematic equation for this, but I think I like this one better because it looks more like a Cal3 equation. It feels like a Cal3 equation. Oh, so what's B not in this case? 1,500 feet per second. So 1,500 feet per second. Let's see. Alpha is gonna be what?
Not 30 degrees.
30 degrees. Okay, all right. So we can say what 5 or 6 we go down to. Try to sound like we're using polar coordinates. It sounded cool. We're part of the cool kids of the block. What else do we need?
My definition of cool.
The height's gonna be what, 200 feet?
I guess we're using 30 per second.
Yes, and that's gonna be gravity. Gravity is going to be 32 feet per second squared, not second. 'Cause feet per second will be velocity. All right, and what do we do? Fluid. So we're gonna have, we'll say R of pi over 6 is gonna be equal to, we're gonna plug in B naught is gonna be 1,500. Cosine of pi over 6 T of I plus oh, we're getting a phone call talk still. Okay, make you go. Oh. So it's gonna be H, it's gonna be 200. plus V naught's going to be 1500 again, right? And then sine of pi over 6. T minus, so 16t squared. Of J. And now cosine of pi over 6 is what? Root 3 over 2, so we're gonna have 1500. And we could do what 750, right? 750 root 3 of t. T I maybe plus that's gonna be 200, and then we're gonna have that's just gonna be 750, right? Sine of pi over 6 is 1/2. Half of 1500 is 750. 750t. No, wait, hold on. Listen. No, it doesn't leach it. There's gonna be 200 plus 750t minus 16t squared of j. So far, so good. So this right here is a quadratic function. This right here is what? Linear. Kind of linear, right? Pretty much. So let's see. What's gonna happen here? So this right here is what? This is the I component, right? So they mean this is the x. No, this should be the.
Oh, right, sorry, of course.
Yeah, that's gonna be the parabolic like this. Yes. This is the thing that the guy did. He shot it in the air and he came back down.
That's like from into the grill.
Yeah, from Hilton in from that man to the grill. Exactly. That's the one. So if we want to find when it hits the ground, what are we going to do?
So y equals 0.
So where the 0 solve the equation and you get a nice number. So you guys need me to do that for you, or you think you can handle it? You can handle it. Perfect. You handle that. And you want to find the max range, what are you going to do?
You plug in that value of t
Into x. Perfect. So when it hits the ground, so we'll say 1 set equal to 0. And so 2 to get the max range. Take previous and plug her in. We'll find the max height, what do we do?
That's y prime.
So find y prime, aka the derivative, and set the derivative. And you want to find the impact velocity of the
I mean, it's actually gonna be the same. Because you started out and then, I don't know,
we ended up lower, so it's gonna have more than
that was right.
Just you plug in the time that it hits the ground, you plug that value into the derivative y prime.
So you have y prime plug in. Which value, Mr. Derek?
T when y is equal to 0.
T when y is equal to 0. I'm rushing, I apologize. I just want to get to the directional group. Okay, so just so you have something to work work backwards on it. T comes up to 47.1 seconds. The max range, ooh, that's 61,185 feet. The max height is going to be 8,989 feet. And then the impact velocity is going to be, let's see, 1,503.61 feet per second. And of course, that's a face value because of why? Why is this face value? Not only that, why is it a face value?
Now, which value?
This guy. This is a face value because of what? It's going faster than when it initially shot out, which means it's not taking something into consideration. What is it not taking into consideration? Air resistance. Air resistance is going to slow that bad boy down. So we'll say big guy. Big.
But also like. At that range, that's a lot of feet, and also like. The Coriolis effect of like the earth is turning out also impact it a little bit.
Yeah.
So,
I'm not sure if I told you about time travel. Did I tell you guys about time travel? And if you were to time travel now and you could go back to the same location you were in like 1700s, would we be on Earth? No, why not? Somewhere else, because what happens is the Big Bang happened, right? The Big Bang happened, so the entire universe is expanding. So it's still expanding. We're close on that. So it's still expanding. So that means that the location where it was in 1700 is going to be different than the location where it is in 2021.
yeah, but isn't it like expanding really slowly?
It is,
Instead
it
of
is,
coming
but-
back here, I'll come back like over by the door.
There won't be a door in 1700.
No, but I'll be like, the distance would be like, oh, it's like 50 feet away.
If you land on the same year, same part of the year, same
Yeah,
day,
yeah.
you'd have to like. Earth is spinning a lot.
Yeah, cause also you would be like, the earth could be here, and then you come up like, you know, like.
Opposite sides of the
it's
sun
like-
from
yeah,
there,
exactly.
that,
Yeah, well, yes. So there's a lot of like crazy things that happens in time travel movies. So a DeLorean going back to time is a little far fetched. You probably want a spaceship instead.
But still, like, if you went back in time, you know, if someone's smart enough to figure out time travel, wouldn't they also be smart enough to figure out that you gotta move? You know?
I'm not sure
Yeah,
Doc is
yeah.
that smart. No. Actually, my favorite show for time travel will always be Doctor Who. Oh, does anyone watch Doctor Who here? Right?
Oh, I forgot that.
You said the 100 was garbage, so I'm not taking your opinion.
No, I'm not saying that it's garbage, I just said I watched episodes, but there's so much.
It's okay, I'm gonna make sure I put that on final. Is the 100 garbage? And the answer is going to be what?
No,
No, you get 10 points for it.
That'd be good. You're getting this ace.
No, you won't get this today, but you'll get 10 points. If the question is used. Key thing is if the question. Alright, so we saw partial derivatives. We saw, what else did we see? We saw the cross, wow, cross product, we had the cross product. We had dot products. We had vector value functions. We had derivatives of the vector value functions. We had functions of several variables which produced partial derivatives. And you had a chain rule, you had limits appear, you had everything appear. Now, we're going to do is we're going to take those ideas and we're going to apply it to everything. What we're going to have is something called a directional derivative. Let's see, let me try to spell this word right. Don't judge me, guys. I think that comes with being a bad professor. You just forget how to spell words. The reason why we forget how to spell words is because we stopped using words in most of our truths. We use symbols. We're gonna look at directional derivatives. What do you think a directional derivative is going to imply? Derivative with a direction. Something with vectors. Why do you think something with vectors is? Ah, I love it. Wow. Good job. I'm proud of you today. Oh, that was beautiful.
I just stated with a vector line,
I know, but
and then below, yes.
either you read the book or you just know what's going on. And I like the second one. I like the latter. You didn't read the book, you just know exactly what's going on. So, oh, this is really bad. XYZ axis. So let's just take a function. Really bad function. And what we're going to do, this is what we're going to do, what I was saying before. So we'll have a point here. And we'll call it point P. That's going to be a point, we'll probably even put the point on the XY plane. What's going to happen is we're going to have a corresponding point somewhere higher. Doesn't matter where it is, it's just somewhere higher. We'll call it point P prime. Then what we're going to do is we're going to have another arbitrary point we're going to call point Q. Point Q is going to have a corresponding point right here called Q prime. So what we're going to see is we're going to have a secant line right here. It's going to be a line of secant. And like we've done before in single variable calculus, like we've done with vector value functions, like we did with partial derivatives and everything, we're going to take one of those points and do what to it? Make it approach P, which is going to produce what? So for now, a limit. And what we're going to try to do is we're going to try to fit this definition into a limit. When we fit that definition into a limit, it's going to give us a directional derivative. Here's the thing, when we're doing partial derivatives of those multivariable functions, we basically looked at the x direction, right? And the y direction for our partial derivatives. Guess what we were doing the entire time? We're doing directional derivatives. We're doing a special case of directional derivatives. Now, when it comes to the directional derivatives, what we're going to do is we're going to do exactly what Jace just told us. What did Jace tell us? That made me smile. Something about vectors. What did we just talk about in those crazy examples with the curvature and the T and B frame? We're looking at what type of vectors?
Unit vectors?
Unit vectors. Technically, in a way, isn't it safe to say if we're taking a secant line or making an approach as close as possible, that is a fraction or even a unit vector itself? That's safe to say, right? So that's what we're going to look at. We're going to look at these unit vectors. We're going to get them infinitesimally close to that point, and we're going to find a directional derivative with respect to a unit vector. And we can find we can even find a T and B of everything just with directional derivative. So it's everything is now coming together as one unified idea. Any questions about that? I feel like a crazy Einstein. My hair is all flying around. You guys are like, yes, professor. I agree. And you all have German accents and everything. Whew. Okay. So what we're going to need, so we're just going to say stuff we need. We're going to need a unit vector. And if we have a unit vector, we're also going to need something very specific. What do you think is that specific thing that we need? Scalar, aka a point, right? We just need a point. So we just need to find a point. But the point is going to be very, very specific. So we'll say, this is what I mean by specific. We're going to do is we're going to base everything on these points right here. Here's the thing, whatever we do to these 2 points happens to what? These 2 points, right? Whatever we do in this world happens in that world. That's a good thing. So what we're going to do, we're going to make a line. When we make a line, we're going to make a line through. And going to have P. And we're going to make an arbitrary vector, which we're going to call U. We're going to make sure that those two are parallel to each other. And what's going to happen is this.
Is that a line through P in the origin or P in Q? Like, what do you mean by line through?
So if we're going to make it to a unit vector, that bad boy's coming from where? Oh, wait. The unit vector is not going to imply that it comes from the origin.
Just a line through P and the origin.
You're gonna parameterize it.
Yeah, we're going to want that line to be P going to P.
Okay.
And then going to be another arbitrary one, which is going to have a U. We don't want it to be the same thing, so it's going to be another line that's arbitrary of it, that's going to be parallel. Okay, perfect. All right, that makes a lot more sense to me. Okay. We're going to make this line through P and through Q. And so whatever happens here happens up there. So it's going to deal with, this is in the XY plane. Whatever's happening up here is, it could either be in the X plane or the XZ plane, or it could be happening in the XY plane. And like we originally did before, we're going to take the partial of the x, and if we take the partial of the x, it's gonna be something in which plane? The x and z plane. If we take the partial of y, we're gonna be in the y-z plane. So what we're doing is we're going to fix these points. It's gonna give us something in this plane right here, if that makes sense. The xz plane. And if we do the other one, of course, we're gonna get something in the yz plane. That's what is gonna make it its directional derivatives. Hopefully that's making sense. Perfect. And if that's happening, well, technically, aren't we producing a delta x in a way? Some change in that x? And then this right here is gonna be some change in that y. And with these ideas, what we're going to do, we're gonna look at that perturbation in a specific limit. So we're running out of time. Let me give you the punchline. What's going to eventually happen is we're going to get the limit as h approaches 0 of f of x plus some height times some u 1. Actually, this was yeah. Comma some y plus some h u2. Close that minus the function itself, all of it divided by h. Now what we're creating is this this shift here, but this shift has a specific height. This shift is going to have also a specific height. So that's where that h is coming from. And this, you can think of it as parameterizing your curve. That's just like the you're fixing it, or you're fixing some type of perturbation. So far, so good. Is it making sense? It's not making sense. What's not making sense, Mr. Joe?
All of it,
All of it, okay.
it's fine, you can keep that.
No.
We've almost gotten it from the limit form to a derivative form.
Yeah, so we're almost there.
Yeah.
So it's going to, let's see, it'll probably make more sense on Tuesday.
Yeah.
So here's what I'm gonna do. I'm gonna stop here. That's okay with you guys, before I keep confusing you more. We'll stop here. We'll pick it up on Tuesday, and we'll go through it in a nice way. Directional derivatives will still be on your test, because the math behind it is extremely easy. You guys know exactly what you're doing, and just the theory behind it. You want to make sure we get that theory. The reason why we want to make sure we get that theory is because when you're taking differential equations next semester, depends on how deep Eric wants to go into the differential equation, that he can do partial differential equations. And these ideas are going to appear there. Yeah.
Okay. So for the test, it's gonna be whatever we covered on Tuesday, and then TNT frames.
Yes.
Okay.
So it's going to be not that much information, but hard test.
Maybe and Arclay.
Yeah, ArcLink is also going to sneak his way into there.
Will there be projectile stuff on the?
Yeah, I can throw a projectile mode. If there's anything, maybe I should make sure we have a lot of projectile motion problems, right?
As long as they're not hard.
No, because, well, the one we did was that hard. Was it that hard? No, so I think you got your hand. And then I go, I will definitely do the practice. Practice stuff I'm gonna do tomorrow, because I'm going to go watch Eternals tonight. And I don't want to go watch Eternals.
I literally just sat there.
Have to go home and get a costume.
All right, hasta luego. I will see you guys Tuesday.
Hey, Professor, I think the section with projectile motions, the homework is locked.
Is locked. I will unlock that bad boy for you.
Okay.
Don't
Thank you.
worry. You're welcome.